Okay, seems to be working. Let's start talking about angles. So most of you probably seen angles before. Let's take one like this. Let's make these rays. Actually, maybe take off my mask because you guys might not be able to hear me in the video. We have a terminal side. Terminal side. We have an initial side. And this point here is the vertex. Okay. Now, usually we start measuring these from the x-axis. So this is the initial. When we do them in the coordinate plane. So we start there, right, and then it kind of swings around counterclockwise. So if this goes up halfway here, so now we're talking about a 45-degree angle, right? That 45. If I go all the way to the y-axis, then from the initial side all the way to the y-axis, and that would be a 90-degree angle. Oops, got my degrees, and so forth. Okay. So if I go all the way to the other side of the x-axis, from here all the way here, now we're talking about 180 degrees. And of course, I can do this all the way till I go a full circle, right? A full circle would be how many degrees? 360, good. Now, all the way around 360. Good. Now, in trig, we often use radians. So what is a radian? So a radian, let me draw you a picture. I think this will be better than the definition. So say we have this. So say that this length here, we know that's the radius, right? Because it's we have a circle. The origin is in the middle of the circle, and the distance from the middle of the circle to the circle, right, is always the radius of the circle. So we have two radiuses there, that one and that one. Now, the angle here, theta, that's created when we intersect a distance over here on the arc that's also equal to the radius. That is what we call 1 radian. Right, so arc can be different, right? Arc can be 10 feet. Arc can be 2 inches, right? It can be a lot of different lengths. But when all those are equal, the angle created by that figure you see, the angle in theta, that's 1 radian. Okay, so that's what they mean by radians. Now, 360 degrees is equal to 2 pi radians. Which means 180 degrees is just 1 pi radians. So what would be 90 degrees? Pi divided by 2, good. 45 degrees? 4. Good. Let's do, what about 0 degrees? How many radians? Any guesses? 0, good. So yeah, 0 degrees, right, means we're at that positive x-axis and we haven't raised that bar at all, right? The terminal side is on top of the initial side. So we're not measuring any angle, so it's 0 for both. coterminal angles. So remember, we said that an angle has a terminal side, it has an initial side, and a terminal side, right? So terminal side is where the angle stops, right? Where you stop the bar and then you measure the angle. So coterminal angles are all angles that have that same terminal side. So for example, if I measure an angle from here to here, let's say it's right in the middle of that quadrant, so that's 45 degrees. But that angle has the same terminal side that if I were to go all the way around and then stop at that same place. But the measure would be different, right? This one we said would be 45 degrees, or pi over 4. But this one, because I went all the way around first, that's already 2 pi. So I went all the way around, that's already 2 pi. Plus, I went pi over 4 more, right, to get to that same ending, same terminal side. So that would be this much, right? What would this be if I add these together? 9 pi over 4. Good, so the 2 pi basically becomes 8 pi over 4, right? And this is already pi over 4. They already have the same denominator there. In case you're wondering how I got there. Good. What is it in degrees?
95.
So we went
405.
405. Good. So we went all the way around. Good. And then 45 degrees more. Good. Now, we know 45 degrees is pi over 4. We know 9 pi over 4 is 405 degrees. How do we convert from one to another? When we're only given those measures. Converting from radians to degrees. So let's check our answer, right, by doing a conversion. So this is 9 pi over 4 radians. We want to convert to degrees. So we're going to multiply by 180 degrees for every pi radians, right? That's what we said earlier. 180 degrees is the same as pi radians. And then we work this out. Notice there's a pi on top and a pi on the bottom. So those are going to divide out to give you 1. And then we got 9 times 180 over 4. What is 9 times 180? 1620 over 4. That gives us 405 degrees. Make sure you keep track of whether you're going to degrees or radians, because the units will be important. Okay, so when it's degrees, make sure you put the little degree symbol on your final answer. When it's radians, make sure you do not put the degree symbol. You can put radians or you can put nothing. So normally what they do in a lot of these textbooks, because not all radians will have the pi, sometimes they'll multiply the pi out so you won't see the pi. Does that make sense? So sometimes it's a whole number. So if the number looks like a 3, for example, like a basic 3, and it's radians, then they'll put radians next to it, like 3 radians. But if the number is something like the angle is something like 2 pi over 3, then the pi kind of lets us know it's radians, so you don't have to put radians. Does that make sense? But if you want to be safe, put radians when it's radians. And make sure you always have the degree symbol when it's degrees. How do we go the other way?
The reciprocal.
Good. Convert from degrees. Good. So we have degrees, and we want to multiply by it's pi radians for every 180 degrees. So this would be 405 pi over 180. So you got that fraction of 405 over 180. So then, you start reducing it. They're both divisible by 5 or whatever you find. Keep reducing it all the way down till you get 9 pi over 4. So there, because I have the pi, I usually don't put radians because I know it's radians, right? Because it's kind of obvious there. But you can put radians. And that's the same way you'll convert any angle from radians to degrees and from degrees to radians. This one is example 5 of the book. Arc length. Now we have a circle. Radius 4. Let's see. This angle here is 240 degrees. And what we're looking for is this arc length outside. Let me see. Okay. We have a formula. For a circle of radius r, a central angle theta intercepts an arc of length s given by this formula you see there. S equals r times theta. Where theta is measured in radians, so that's important. Theta is in radians. Note that if r is equal to 1, then s would just be equal to theta. And the radian measure of theta equals the arc length in that case, okay? So we know r is not 1 here, right? R is 4, so we'll have to plug in the values to find the answer. So if I'm looking for s, r here is 4, good. And it's actually 4 inches. 4. And what is theta? 240 degrees. Can I plug that in?
No.
I have to change it to what?
Radians.
Good. So be careful with those. I always have people miss these on the exam. And mainly it's just because they plug in the degrees instead of plugging in radians. So convert this to, to multiply here. So we multiply by pi over 180 degrees. So we got 240 pi 180. Then start reducing. What goes into 24 and 18? Oh, 6? 6 goes in 4 and 2. Is that right? Oh, 3. Thank you. Can we reduce any more? No, right? 4 and 3 are relatively prime, so that's the angle that we're going to put in here. All right, so we multiply 4 times 4/3 pi. So remember, 4 is like 4 over 1, basically. Got 16 over 3 pi. This would be the exact answer. If your problem asks you for a decimal approximation, then you can work it out. So you would do 16 times pi, right, in your calculator, and then divide by 3 to get sort of a decimal approximation. Now, we're almost done. What do you think the units are here? Because we are talking about a length, right? So we need units. So in this case, because the radius was 4 inches, then this will be in inches also. Okay. So this is the arc length. If I multiply this out, you would get about 16.76. So be careful on the way you give your final answer, especially in WebAssign. If it doesn't mention anything about rounding the decimal, then they want the exact answer. Okay, so you would enter it as 16 over 3 pi. But then if you see something that says, round to the nearest hundredth or something like that, then that means they want you to multiply it out and give a decimal. Let's see. This one might be, let's save that for later. Let's move on to 4.2. So you'll often hear people talk about something called the unit circle. So it's a circle centered around the origin. And the unit part comes because the radius is 1. So this point would be 1, 0. This point would be 0, 1. Negative 1, 0. Negative 1. Let's see. Okay, let me bring up a picture for the whole thing instead. Okay, and this is what we can create from it. Notice the points they have on the ends. So the 1, 0, right? And then from this, they break it up into 30, 45, 60, 120, 135, 150, and so forth all the way. And notice they can tell us where these points are, right? So where this intersects the circle, This is that point on the grid. Does that make sense? So on the grid, right, we're still in the Cartesian plane. This point is that point. This point is that point. This point is that point, and so forth. Okay. Now, how will we use this? See, I can find a better one. It's hard to see. Okay. Now, let me give you some definitions for the trig functions here. So these are the trig functions we'll be using pretty much all semester. And how they're defined by the unit circle. We have sine of some parameter is equal to y. So by y, they mean the y coordinate in the point. The points we were looking at that were on the circle. So sine is given by the y value. Cosine is given by x. Cosine of t is equal to x. Tangent of t is equal to y over x. Of course, x cannot be 0, right? Because we can never divide by 0. The reciprocal of sine is cosecant. That's 1 over y. Of course, y cannot be 0 because it's in the denominator. Secant is the reciprocal of cosine, so it's 1 over x. X cannot be 0. Cotangent is the reciprocal of tangent. So cotangent of t is equal to x over y. Y cannot be 0 because it's in the denominator. Okay, so sine, let's start with sine. Sine of something, in this case t, sine of t is equal to y. So that's the y value, right? So the t represents the angle. How do we do this? If you say sine of pi over 6, that's this one, sine of pi over 6. Which one of these is the y value? 1/2. So sine of 30 degrees is equal to 1/2. Does that make sense? What is sine of 150 degrees? Also 1/2. That's the y value for 150 degrees. Sine of 300 degrees. (300), which is the same as 5 pi over 3, would be negative square root of 3 over 2. Does that make sense? So the y values give you this, what the sine is of each of those angles. All right. What about cosine? Cosine is the x value, as you can see there. Cosine is the x value. So cosine of 120, for example, would be negative 1/2. Cosine of 4 pi over 3, negative 1/2. Cosine of 270, 0. Cosine of 90 degrees, 0. Good. Tangent. So tangent, you will have to do y over x, right, to find the tangent of something. So you'll have to take the two values and put one on top of the other one. Y over x. Tangent, oops, there we go. Tangent of 45 degrees. Yeah, because it's what? It's square root of 2 over 2 divided by square root of 2 over 2. Same number, right? So you get 1. Good. Tangent of pi over 2. Undefined, because y over x would be 1 over 0. And remember, they said the denominator cannot be 0, right? So it's undefined. So there's no such thing as tangent of 90 degrees. Okay. Tangent of 180. Yeah, 0 over -1 is just 0, right? Any questions on how that works? So as you can see, cosecant is just the reciprocal of the sine, right? So if sine of pi over 6 is 1/2, if sine of pi over 6 is 1/2, what would be cosecant of pi over 6? 2, right? So you take the reciprocal of the sine. 1 over 2 becomes 2 over 1, which is just 2. Good. Cosine of 5 pi over 4. Cosine of 5 pi over 4, that's 225 degrees. What is cosine, x or y? X. And here it doesn't matter, right? They're the same. So it's going to be negative square root of 2 over 2. Negative square root of 2 over 2. What would be the reciprocal? What would be the secant of 5 pi over 4? What do I do to this? Reciprocal, good. What's the reciprocal? Good. The only issue here is that we have a radical, right, in the denominator, and when that happens, you should keep simplifying. How do you do that? How can I get rid of this square root on the bottom? Multiply by? The same thing, right? So basically we're multiplying here by 1. Right? This is allowed because I'm not really changing anything, right? I'm multiplying by 1, and when you multiply by 1, it doesn't change anything. It doesn't do really anything. It just might make it look different, but it's still the same value. So we multiply by 1, but notice what we get here. On top, we get negative 2 square root of 2. And what is square root of 2 times square root of 2? That would be dividing. What do we get if we multiplying? Square root of 2 times square root of 2. 2. Good. You can also think of it like this. Square root of 2 times square root of 2 is equal to square root of 4. And that's, of course, 2. Am I done simplifying? Can I do anything else? Yeah. There's a 2 up here and a 2 down here. They divide out. So we end up with negative square root of 2. So be careful on some of those. On some of them, it's easy just to take the reciprocal, but remember that when you do end up with a radical in the denominator, you will have to simplify that. So run out of space for tangent. Let's do it down here. let's say tangent of y over x. Oh, this is pi. Tangent of pi. Tangent of pi is 0 over negative 1. Y is 0 and x is negative 1, which of course we said earlier was 0. So what would be cotangent of pi? Good. So reciprocal of 0 over negative 1 is of course negative 1 over 0, right? Which is undefined. All right, let's try a negative angle here. What about sine of negative pi over 3? Sine of negative pi over 3. How do you think we would measure negative pi over 3? So positive pi over 3 is easy, right? We would just go up that much. This would be positive pi over 3. Which is the same as how many degrees? 60 degrees? That's positive, right? But this is saying negative pi over 3. So for negative, we started our initial side, and then we go, instead of up, we go down that much. Does that make sense? So we would actually go down that much. But instead of calling this negative pi over 3, we would flip it around and do the positives the other side, right? So we would say, okay, what's the angle to go from here to here? What do you think? If the whole circle is 360 and I'm taking away 60 of it, what's left? 300? Does that make sense? And what is 300 in radians? We could just convert. Uh, 30 and 18 are both divisible by. So we know 300 is also 5 pi over 3 radians. So these two are coterminal, right? So negative pi over 3 and 5 pi over 3 are coterminal angles. So earlier we were saying coterminal angles share a terminal side, right? They take you to the exact same place, but they can look different, right? They can have different values, but they take you to the exact same place. So that means that instead of worrying about sine of negative pi over 3, now we're going to worry about sine of 5 pi over 3. And remember, sine is the y-coordinate. So let's see what the y-coordinate is for 5 pi over 3. 5 pi over 3. Negative square root of 3 over 2. negative square root of 3 over 2. Any questions on coterminal angles or finding sine, cosine, tangent?
Yes.
Yes.
When you're multiplying the 300 times 1 over 180,
Yes.
where that come from?
Oh, so this is for, we wanted to convert it. So with this, we use this to convert to radians.
Oh,
Does that make sense?
yes.
Good question.
So it's always going to be the pi over 180?
Yes. Yeah, and then 180 over pi to go the other way. All right, so there's another way we could have done this, and we would need to use what they call even and odd trig function definition. Let me see, how do I write this out? Let's do it like this, even. So these definitions tell us that because sine is what they call an odd function, sine of negative parameter is equal to -1 times sine of the positive parameter. So what does that mean for our previous example? So that means that earlier when we had sine of negative pi over 3, sine of negative pi over 3, we could have also changed this to negative sine of positive pi over 3, and they would be equivalent. So we'll check right now and we get the same answer. So for negative, so read the second one as -1 times sine of pi over 3, basically. So we took the negative, is no longer inside the angle, right? Now it's out front. But what this allows us to do is we can just find sine of pi over 3, like we normally would, and then just multiply it by -1, right? So this would be equal to, what is sine of pi over 3? So pi over 3 right here, 60 degrees. Sine is square root of 3 over 2 times the negative in front. Good. So we see we get the same answer, right? As we got up here when we change it to 5 pi over 3. So remember some of these even odd definitions, you can probably work faster. So sine is odd. What else is odd? So sine has a reciprocal, right? The reciprocal is cosecant. Good. Okay. So cosecant also. This will also be given by taking the negative out front and then changing the angle to a positive parameter. Tangent is also odd. You can also do this with tangent if they give you a negative angle. And of course, the reciprocal of tangent follows along. Cotangent. Now, the one missing is cosine, right? cosine and its reciprocal. So cosine is even. Cosine of a negative angle is equal to just cosine of the positive angle. And the reciprocal follows along. Secant. So in other words, if they were to ask you to find cosine of negative 5 pi over 4, you could just find cosine of 5 pi over 4. That would be the same thing. Now the reason cosine is even, if some of you may recall from pre-cal 1, there was a whole section in there about even and odd functions and how to figure out if a function is even or odd. It's even if the graph is, well, one way to tell, right? You can do this algebraically too, but graph-wise, it's even if the graph is mirrored over the y-axis. Does that make sense? So it's reflective, it reflects over the y-axis. That's when you know if something is even. Cosine graph. If we don't remember, is like this, right? Like that. So notice how you can fold it over the y-axis. So that's how we know that that one is even. So in case you ever kind of want to remember which one is even, and just remember cosine is even, because it's really obvious from the graph. Everything else is, all the other trig functions are odd. So just cosine and its reciprocal, of course. Okay, what about larger angles? Example 2. I feel like it's missing something here. Let's do sine of 13 pi over 6. How do we find this, right? So sine of the angle is 13 pi over 6. If you notice, if you're looking at the unit circle, we don't see any 13 pi over 6, right? Anywhere. So that means you have to break it down a little bit. Oh, you can't see because it's shaking a lot, but it must be the system in this room, because the other classroom, it was steady the whole time. So 13 pi over 6. Because it's bigger than 2 pi, remember the unit circle is only one revolution, right? So that's only 2 pi that it goes up to. So 13 pi over 6 is bigger than 2 pi. So that means you have to kind of break it down a little bit. So how can we think about 13 pi over 6? Well, how do we get 2 pi with a denominator of 6? That would be 12 pi over 6. And to get to 13 pi, I would have to add another pi over 6. Does that make sense? So you kind of have to break these down. So 12 pi over 6 plus pi over 6 gives us 13 pi over 6, right? So that's a true equation we have there. Why 12 pi over 6? Because 12 pi over 6 is the same as 2 pi, right? So this, same as 2 pi. Why does that help us? Well, it helps us because 2 pi is something very easy to find, right? It's a whole revolution. So if I want to find 13 pi over 6 on here, and I want to find the coterminal angle that matches that, I know I have to go 2 pi, so all the way around, 2 pi, and then pi over 6 more. So the angle is here. So we went 2 pi, a full revolution around from positive x-axis to positive x-axis, and then we still had to go pi over 6 more. So then we keep going pi over 6 more. So now that angle, this new angle, is the same as 13 pi over 6, right? But we can just use pi over 6. So instead of using 13 pi over 6, we can change this to just pi over 6, okay? And of course, pi over 6 is easy. That was one of the ones that's in our unit circle, right? What was its sign? So the y value is 1/2 for that one. So you might need to do this. Sometimes the angles get really large. So in this case, we were able to break it down to 2 pi plus pi over 6. But sometimes you might break something down to like 10 pi plus pi over 3 or something like that. So 10 pi is how many revolutions around? 5, yeah. So in that scenario, right, 10 pi, well, let me actually do it here. Do a side note here. This would be sine of, let's say, they gave it to us like this. This would be the same as sine of pi over 3, right? Because those 5 revolutions would be 1, 2, 3, 4, 5, and then pi over 3 more. So something like that. And then of course, sine of pi over 3 is just square root of 3 over 2. Like that, all right? Remember that sometimes you might need to do half turns. So for example, sine of, let's do 13 pi plus actually no, this is too big. Let's just do, let's save the confusing ones for later. Let's do this one's a little less confusing. Let's say you had to do 13 pi plus 3 pi over 4. Just in terms of finding where the quadrant would be. Where would this be? So 13 pi would give us how many full revolutions? 6 plus half one, right? So 6 full ones, good. And then another half. And then the 3 pi over 4 still, right? So it would be something like 1, 2, 3, 4, 5, 6, and then half. And then still 3/4 pi. So what quadrant would that put me in? So notice if I go all the way around again, that's 1 pi, yeah. And 3/4 pi is less than 1 pi. So yeah, I would put us somewhere over here. Does that make sense? So our angle would be somewhere here. Let's try B. B is a cosine of negative 7 pi over 2. What can we change this to? First of all, is cosine even or odd? Even, good. Even means that we can drop the negative sign, right? So we can just work with positive 7 pi over 2. How do I find 7 pi over 2? So how can we break this down? 7 pi over 2 is the same as, how do I get 2 pi out of this with a denominator of 2? So 4 pi over 2, that's the same as 2 pi, right? So that's 1 full revolution. But how much more do I need to get to 7 pi over 2? Oops. 3 pi over 2, good. Yeah, that works, right? 4 over 2 plus 3 over 2 is 7 over 2. So we have the right breakdown here. Now let's see if we can figure out which quadrant the angle would be in. So 4 pi over 2, that's just 1 full revolution. So we go all the way around once. And then how do I do 3 pi over 2? What is, yeah, how far do I go? Oh, and for those of you that don't quite see it, remember that you can also change these to degrees if you want at any point. So notice this would be which is what, 3 times 90? $270. So this is, think of it this way. This is 360, and this is 270, right? So 360, that's this part. And then we go 270 more. So 270 is what? 90, 90, 90. So right here. So because that brings us to the y-axis here, you'll be using the to find the cosine. You'll be using the point, this point, the 0, -1 point down here on the unit circle. That's what you would use. So what is the cosine, x or y? X value here is 0. So this would be 0. Okay, so keep that in mind. If you prefer to work in degrees, you can. Just make sure you convert back to radians in the end, in case the web assignment is asking for radians. Let me see. That takes care of 4.2. Let me see if we missed something from 4.1 real quick. Linear speed. All right, let's try example 6. So going back down. You won't see very much of this, that's why I wanted to cover the more important stuff first, but just so that you've seen everything. There's a couple formulas here they give us. One is for linear speed. That's a curly V, and this is the formula. V is in velocity, but this is for linear speed. Arc length divided by time. So remember, arc length was S, and time, of course, is T. A particle moving at a constant speed along a circular arc that has radius r. If S is the length of the arc traveled in time t, then the linear speed v is given by the formula you see there. Moreover, if theta is the angle in radians corresponding to the arc length that the particle is traveling on, so think of like earlier we looked at a circle, right? So this is the arc length, right? So it might be traveling on this piece or maybe a larger piece or something like that. If theta is the angle corresponding to the arc length, so in other words, if we're talking about this arc, then they're talking about this angle theta for that arc length. So we do have a theta, then the angular speed is equal to central angle meaning theta, divided by the time. So this is just theta over t. So we have S over t and theta over t. S over t is linear, theta over t is angular. And this is a couple of examples here.
Are you doing this? Robert, yes, I am.
All right, let me read you the problem. The second hand of a clock is 10.2 centimeters long. Find the linear speed of the tip of the second hand as it passes around the clock face. Okay, so there's a clock. And it's giving us the time. So these are the main hands. And then there's a little in here. This is 10.2 centimeters. Find the linear speed of the tip of the second hand as it passes around the clock face. So in one revolution, how far does it travel? In, let's say, should we do it this way? Yeah, that's, no. Okay, yeah. So let's do this. Let me write it out. In one revolution, the arc length traveled two pi r. So 2 pi obviously because we're talking about a whole revolution, right? 2 pi all the way around the circle. The length of that second hand, 10.2 centimeters. So that's our radius, right? 10.2. Remember, it's in centimeters. If I keep the pi in, right? So we won't multiply it out. This is multiply the 2 and the 10.2. So we got 20.4 pi, and this will be in centimeters. Does that make sense? So all the way around, right? We're looking for that arc length. When we make a full revolution, that's how far we would travel, all the way around. 2 pi r, what formula does that remind you of when dealing with a circle? 2 pi r, you remember?
Diameter?
Not diameter. What do they call it, the distance around? Circumference. Yeah, so remember circumference is 2 pi r. So that's where it came from, right? Except instead of circumference, we're calling it s, because we're calling it the arc length that we're traveling. So it's like we're traveling all the way around the circle, right? So that's why we're using it. So we were just looking for the distance around the circle, basically. Well, actually clock, I should say. Now the second part of this is the time required for the second hand to travel this distance. How long does it take for that second hand to go all the way around? Because that second hand measures what? The main two hands is what? Hours, minutes, and the second hand is seconds. So to go all the way around, how many seconds is it? 60. 60 seconds, good. So that's our time. Let me do this. 1 minute. 60 seconds. Good. So the linear speed because remember for the linear speed the formula was s over t. And now we have s, right? S is the distance around the clock. Divided by time. Time. In this case, let's use 60 seconds. If we divide this out on the calculator, we will get about 1.07. And remember, the units tell us what to put. So we took centimeters and divided by seconds. So it's centimeters per second. So the linear speed of that second hand is 1.07 centimeters per second. But this linear speed stuff, I just wanted to do one quick one because you really only see it in this section, this chapter. But the trig stuff, we're going to see pretty much the whole term, okay? So the most important stuff was the sine, cosine, tangent, all that stuff. The reciprocals, how to use a unit circle, etc. Okay? But just in case they throw one of these at you. So let's stop there.